Hey there, today my team and I will be performing video presentation according to the topic given to us, which is gaseous state. Assalamualaikum and hi everyone. My name is Ahmad Akil Haikal bin Ahmad Azrai, student ID 2024804312 from group RAS 1201C. Today I will be briefing about the subtopics given to me, which is characteristics of gases and gas laws. I will be starting off with the characteristics of gases. There are many characteristics of gases. One of them is they have no fixed shape. Gas fills the container it occupies easily. Gas also expands easily. They occupy the entire available volume. Next, gas have low density. This is because the particles are widely spaced and move freely. Other than that, gas is also compressible. They are easily compressed into smaller volumes. Gas have rapid diffusion. Particles mix and spread quickly in gas form. Not only that, gas also have no fixed volume. Gas takes the shape of the container. In addition, gas also exerts pressure. This is due to particle collisions with container walls. And last but not least, there are no attractive force. This is due to the weak intermolecular forces between particles. Next, I will be talking about gas laws, which are Charles' law, Boyle's law, and Avogadro's law. The first one is Charles' law. Charles' law stated that the volume of a fixed amount of gas maintained a constant pressure is directly proportional to the absolute temperature of the gas. As you can see, the formula created by the Charles himself is V1 over T1 equals to V2 over T2, whereby V equals to the volume and T equals to the temperature. Next to the formula, you can see that the graph which proves volume is directly proportional to the temperature. And beside the graph, you can see the picture of the man himself, Charles. Next one is Boyle's law. Boyle's law stated that the pressure of fixed amount of gas at a constant temperature is inversely proportional to the volume of the gas. The formula given is P1V1 equals to P2V2, whereby P is equals to the pressure and V equals to the volume. And this is the graph that proves pressure is inversely proportional to the volume of the gas. And the picture belongs to the Boyle's himself. After that, there is Avogadro's law. Avogadro's law stated that at constant pressure and temperature, the volume of a gas is directly proportional to the number of moles of the gas present. And its formula is V1 over N1 equals to V2 over N2, whereby V equals to the volume and N equals to the number of moles. This is the graph that proves volume is directly proportional to the number of moles. And this is the picture of Avogadro. Next, I will be talking about something additional, which is ideal gas. Ideal gas is theoretical gas composed of many randomly moving point particles that are not subject to the interparticle interactions, which PV equals to nRT, P equals to pressure, V equals to volume, N equals to number of moles, R is gas constant, and T is temperature.
Assalamualaikum. My name is Irfan bin Muhammad Huzaimi. My student ID is 2024662834. My class group is RAS 1201C, and the subtopics that I will be discussing about gaseous state is kinetic molecular theory of gases and deviation of ideal behavior of gases. First, I will be discussing about kinetic molecular theory of gases. Now, there are 5 basic assumptions about the molecular theory of gases. The first one is gases are composed of small particles, either atoms or molecules. The second one is the gas particles are in continuous random motion. Third one, collisions between particles and with containing walls are perfectly elastic. The fourth one is the intermolecular forces of attraction does not exist between gas particles. And lastly, the average kinetic energy of gas particles is directly proportional to the absolute temperature. So here is the formula for kinetic energy of gases that defines all of those assumptions, which is Ke equals 3 over 2 Nk Bt. Ke is the total kinetic energy of the gas, N is the number of moles of the gas, Kb is the Boltzmann constant, with a value of 1.38 times 10 to the power of negative 23 joule slash K. T is the absolute temperature of the gas in Kelvin. Now, deviation of ideal behavior of gases. The ideal gas law assumes that gases behave ideally under any conditions. However, real gases deviate from this behavior. The deviations arise due to the kinetic molecular theory of gases that are not entirely valid for real gases. So there are two causes that causes the ideal behavior of gases to deviate, which is intermolecular forces and finite molecular volume. Now, finite molecular volume means a volume that is limited. The first one is intermolecular forces. In real gases, particles exert attractive or repulsive forces on one another, and these forces are significant at, firstly, high pressure, because the particles become way closer together, thus increasing the attractive forces between particles, and secondly, lower temperature, making the particles move slower, thus having lower kinetic energy, allowing attractive forces to affect more between particles. The second cause of deviation of ideal behavior gases is finite molecular volume. In ideal gases, the volume of gas particles is considered negligible compared to the container's volume. However, in real gases, particles does have finite volume. For example, when the gas particles are stuck in a compressed container, the particles have less space to move in because they take up some of the space in a tight container, making the particles jump off the container wall frequently and vigorously. And due to all those deviations of ideal gas behavior, a scientist named Johannes Frederik van der Waals created a more refined equation for real gases called van der Waals equation, which modifies the ideal gas law to account for intermolecular forces and finite molecular volume. The equation is as shown at the side. And based on those deviations, there are two conditions that we can take from the deviation from ideal gas behavior, which is high pressure and low temperature. For the high pressure, gas particles are compressed into smaller spaces and the finite volume and intermolecular forces become more significant, and they occupy a greater volume and exert less pressure than predicted by the ideal gas law. Whereas for low temperature, particles have lower kinetic energy at low temperatures, allowing intermolecular forces to occur, and they stick together, causing reducing pressure and deviations from the ideal gas law. And from here we can identify two different gases, which is ideal gases and real gases. Ideal gases are volumeless, whereas the real gases, they have finite volume. The gas particles do take up the space, and the volume of the gas particles are actually less than the container's volume. The particles in ideal gases does not interact with each other, whereas for real gases, the particles do attract each other and also interact with each other. The molecules in ideal gases would travel in straight lines, whereas in real gases, the paths would curve due to the attractions between molecules.
Assalamualaikum and hi everyone. My name Muhammad Zahir bin Khamir, student ID 2024282342 from group RAS 1201C. Today I will share about subtopic has given to me about Graham law of diffusion and effusion and Dalton's law of partial pressure. There are two things I will discuss on Graham law is diffusion and effusion. Firstly, we will talk about diffusion. So the process of gas movement of one gas through another. Diffusion also can be said as the spreading of particles from a higher concentration area to a lower concentration area. In this slide show an example of diffusion. Secondly is effusion, the process by which a gas escapes from its container through a tiny hole into an evacuated space. This is a formula for a rate of effusion, 1 over square root m. Formula for effusion is rate A over rate B equal to square root molar mass B over molar mass A. And this is an example for effusion. Next, I will share about Dalton's law of partial pressure. The total pressure of a mixture of gases is equal to the sum of the partial pressure of the component gas. This is an example for partial pressure. And beside the example is formula for Dalton's law. Total pressure equal to pressure 1 plus pressure 2 plus pressure 3 and so on.
Assalamualaikum. My name is Muhammad Lomar Hakim, and the topic that I will present is about the application of gases. The first application is industrial application, such as production of chemicals. Gases like hydrogen, nitrogen, and oxygen are essential in chemical manufacturing processes, such as ammonia synthesis in the Haber process. The second application of gases is medical applications. An example is ventilation support. Medical oxygen is used for patients with breathing difficulties. The third one is energy sector, such as fuel. Gases like methane, propane, and butane are used as fuels in home industry and vehicles. The fourth one is environmental applications. Greenhouse gas monitoring is one of the applications. Gases like carbon dioxide and methane are studied to understand climate change. The fifth one is aerospace and aviation, such as rocket propellants. It is known that liquid oxygen and hydrogen are used as propellants in rockets. The last one is food and beverage industry, such as preservation. Carbon dioxide is used for packaging foods and beverages to maintain its freshness.